Essay prompt 1. When beginning to talk about how the heart contracts and everything that goes on, I feel like it is important to take a step back and to not only talk about what muscle contraction as a whole looks like, but to also talk about what a depolarization signal is. So the way that I'll start this is explaining the depolarization signal is effectively an electrical stimulus inside of the body. Now, the important thing to remember is that electricity or electrical stimuli always cause contraction of muscles. They always cause contraction of muscles. So you notice that like when an individual gets tased, the muscle starts to spasm because you're constantly sending these electrical signals which are causing artificial depolarizations of the muscle. It's a similar thing that goes on inside your body, but it happens naturally. So the way that you generate this electrical signal is through your normal cells. And so what you have here is you have your normal cell has a negative charge on the inside and a positive charge on the outside. Now what will happen is in order to cause a depolarization signal, we need to make the inside of the cell more positive, or a better way that I like to think about it is less negative. Make it less negative. So we'll have holes inside the cell membrane that'll allow us to bring in positive ions. Bring them in. So you see over here on this side, we have this diagram. Now this diagram is called an action potential. An action potential is another similar way to think about a depolarization wave. So right here, you're the inside of your cell, very, very negative. It's about negative 70 millivolts. What you're going to do is you'll slowly creep up to this value of negative 55 millivolts. And then after you hit that, a depolarization signal will be sent. It'll come down and hyperpolarize again before going back to this negative 70 millivolts, which is called your resting membrane potential. Resting membrane potential is controlled by bringing in two positive ions and taking out 3. This is what is called your sodium-potassium pump. You're going to take out 3 sodium and bring in 2 potassium. And overall, you hit pretty much a net neutral change in charge. You're not really going anywhere. You're maintaining at about this negative 70 millivolts. And this allows you to maintain a resting membrane potential for your cells until you're ready to begin to create another depolarization by bringing more positive ions in. Now talking about the contraction of a muscle and what that looks like. So if you'll remember from like anatomy and physiology, you have a muscle fiber, and that muscle fiber is wrapped in what is called the sarcolemma. Now underneath your sarcolemma is a set of like wires almost that are called your T-tubules. Now the T-tubules' job is to carry electrical charges. It's to carry the electrical charges into the muscle. So then what's going to happen right here is this channel here represents your T-tubule. And electricity, your depolarization signal, is going to travel down this T-tubule. It's going to come down this T-tubule. Once it gets to a particular spot, it's going to cause what it's called your sarcoplasmic reticulum to release calcium across these little feet-like structures. They wiggle and allow calcium to travel over them and into the muscle. Now, calcium is very, very important for what is called sliding filament theory or cross-bridge formations in your muscles. But the big thing to remember is depolarization signal sent by a cell after having been maintained by sodium-potassium pump, sent by the cell, travels down the length of the T-tubule to this location, causes calcium to be released and to trickle in across these little feet-like structures here and into the muscle. So from there, we have to go and talk about our actual muscle contraction, how we generate force through the muscle. So I'll do this in an explanation here of a rope. So effectively, you have a rope. Now your rope represents actin and your arm is going to represent myosin. Normally, you can't grab on to that rope with your hand. You can't grab onto it just because there's no spot open. So what needs to happen is there needs to be a spot that opens. The spots on actin are blocked by a structure called tropomyosin. Now, tropomyosin has a structure on there called troponin, and troponin has a binding site called troponin C where calcium binds. That's a lot of information, but I'm going to take a step back real quick. Actin, your small muscle fiber, has its binding sites blocked, so you can't cause a contraction, you can't generate force. So you have to move tropomyosin. The way that we accomplish this is by binding calcium to troponin C. Now, troponin C is going to cause tropomyosin to move out of the way, to rotate, and to expose the actin binding sites. Now we go back to our rope diagram. We now have a spot on that rope. We're going to reach up and grab onto that rope. Myosin has now bound to actin. Now, in order to create force, we need to pull. And the way that we do that is by removing the ions that are attached to, or the molecules that are attached to myosin. Those molecules being ADP, adenosine diphosphate, and an inorganic phosphate. So we're held up here. We can remove that inorganic phosphate and pull it halfway. Remove that ADP and pull it completely. Complete that full power stroke that we're looking for. And that is how we initially generate force. Now when we get into heart-specific stuff, since we have the groundwork laid of talking about depolarization and contraction, we can talk about how the heart contracts. So the first thing is, if you remember that diagram I showed you earlier of resting membrane potential, that doesn't exist inside of the heart. If you'll remember, your heart kind of has an automatic pacemaker inside of it. You don't have to tell your heart to beat or to contract. Your heart automatically does it. It has an internal pacemaker that allows it to depolarize at a particular rate. What this looks like in terms of a diagram is that you never have a true resting membrane potential. Instead, you slowly trickle up from like -70 starting up to -55. You send your depolarization wave. You go down into hyperpolarization, and then you slowly begin to repolarize the muscle. Slowly begin to repolarize until you get back to threshold potential, send another signal, send another signal, send another signal. Now, inside of your heart, you have a particular structure called your SA node. Your SA node is what I was referring to earlier when I talked about the automatic pacemaker that you have inside of your heart. It sits up in the top of the right atrium. Up in the top of the right atrium right there, that's where your SA node sits. And what your SA node is going to do is it's going to send a signal. Now, normally, in normal muscle cells, you have to be innervated in order to get that electrical stimulus. The heart doesn't work like that. It doesn't have to be directly innervated. Your SA node is going to cause a depolarization signal, which would normally have to be innervated to other muscle cells in order to make it spread, but not in this case. Cardiac muscle cells are different than either of the other two types of muscle. So it's not like skeletal muscle and it's not like smooth muscle where you have to be directly innervated. Cardiac muscle has what are called intercalated discs, and intercalated discs allow you to spread a signal from one cell to the next. So your depolarization signal is sent. It hits that cell. That cell spreads it to the next cell, to the next cell, to the next cell, to the next cell. And that ends up giving this nice wave-like motion of the electrical charge or the depolarization throughout the tops of your atria. Now, what that looks like is it ends up causing your atria to contract from the top down. Top down. And if you were looking at that diagram, you notice that we have these ventricles down here. Your atria feed into your ventricles. We have to put the blood from the atria in the ventricles. So this works perfect, top-down contraction. Now, the trouble in paradise comes when you realize that you can't send blood down in your ventricles. If your ventricles contracted top down, we would end up in a really bad position, because if your ventricles were contracting top down, then you would not have anywhere for the blood to go. It would just sit in the bottom of the ventricles. You'd just be putting force on the blood. There's nowhere for it to go. So instead, the way that we have to work around this is this wonderful structure that's called your AV node. Now, your AV node sits right in the middle of this layer here. And this layer here is entirely electrically inert or electrically dead cells. These cells cannot carry an electrical charge. So effectively, this charge dissipates when it hits right here, except thanks to this structure, your AV node. Now, this AV node will pick up the signal from the SA node, and it will cause that signal to travel down these structures that are called your left and your right bundle branches, right along the inside wall of the heart. From there, the signal is sent up these fibers at the bottom called your Purkinje fibers. This translation, down and up, allows the ventricles to contract from bottom to top and ring out to get as much blood possible out of the heart. Contract bottom to top in a ringing out motion. So this is really good because it, once again, allows us to get as much possible blood out of the heart as we can. So when we think about how we want to get force put on the blood, because the big thing is, if we go back to the equation that we've talked about of cardiac output is equal to our heart rate times our stroke volume, right here, that Q equals HR times SV, where Q is in milliliters per minute. We then specifically here are going to look at stroke volume. Now, stroke volume is controlled by a couple of things, being preload, afterload, and importantly for us, contractility. Now, contractility is effectively the force that you can put on the blood. It is the force that you can put on the blood, the force that can be generated. If you increase contractility, you increase stroke volume. Increasing contractility increases stroke volume, and by product, you then increase cardiac output. And you want cardiac output to be high. So then you have to increase stroke volume. Now, increasing stroke volume means you have to increase your force. Now, in a normal, healthy individual, you're going to relatively be putting the same mass of blood into the ventricles every time. Your atria will get filled to roughly the same amount. It gets dumped into the ventricles, and you end up with right around the same mass of blood. But what you can change is acceleration. Going back to Newton's laws, we know that force is equal to mass times acceleration. So if we can't affect the mass, we can't affect the acceleration. And this is why we need that signaling from the Purkinje fibers to be so fast. Because if we get a fast contraction, we're going to cause a much greater force to be exerted onto the blood, thus increasing contractility, increasing stroke volume, increasing cardiac output. And we generate force by that fast contraction. Now, if we think about an ablation and how that affects the heart, we first need to talk about what an ablation is. Now, an ablation is very simply going in and using either a heated instrument or a supercooled instrument. You scar the tissue of one particular section, in this case of a cardiac ablation, inside of the heart. Most commonly, you'll see liquid nitrogen being used for the scarring process. The main reason we want to scar it is because scarred tissues do not conduct electricity. Now, you may be thinking, why would we ever want to scar tissue of the heart? That sounds like a horrible idea. We're just going to mess up our heart. And to a degree, you would be right, but there are conditions where it becomes necessary. So there are times when your cells inside of your heart can spontaneously depolarize, spontaneous depolarization. And when that happens, you end up with some bad side effects. Because if you depolarize, thanks to the nature of cardiac muscle cells with those intercalated discs I mentioned earlier, the signal gets spread all the way across the heart. but your SA node, that natural pacemaker, is still firing. So you end up with these conflicting signals, both trying to cause them to contract, and you get all out of whack, and your heart is incredibly out of order. If you go in with an ablation to the area that's causing a problem, that's causing contraction signals to be sent when it shouldn't, you can go in and freeze that area. When you freeze that area, it stops it from being able to send depolarization signals, and thus your heart's normal rhythm is restored as the SA node can take back over again.